Hello, everyone. Hi, so welcome to this last session of the day, Large Language Models with Keras. I'm Martin.
I'm Gabriel.
And I'm Samane.
And we are from the Keras team. And today we would like to take you on a journey through various workflows involving large language models and Keras. Keras is a high-level modeling framework. It's basically what helps you assemble your neural network models out of neural network layers. Our team is also working on two additional libraries called Keras-CV and Keras-NLP, which are two collections of state-of-the-art pre-trained computer vision and natural language processing models. So we want to show you how to handle large language models with those. We'll start with very easy workflows, how to load a model, how to implement a chatbot. And then, since Keras is a full-fledged modeling framework, we will also turn up the complexity a little bit towards the end of the second half of the session and show you how to implement more demanding workflows in Keras. Let's start with Gabriel.
So we're going to be implementing some chat experiences, as Martin was saying, with Gemma. And to set the stage, Gemma is Google's family of these top-performing open language models. These are language models that are able to take text in and text out. So they're what you would use to create poetry, write stories, even talk like a pirate, as we'll show later on. Our release is through this Keras NLP package, our natural language processing version of Keras NLP, that has all of these utilities that we'll explore throughout the session. One important thing about Keras 3, our newest release that came in just a few months ago, is that it is fully multi-backend. So that means that everything we're going to be doing today is going to be available in both PyTorch, JAX, and TensorFlow, all with just a single line of code. So here we see our Gemma implementation for Keras NLP. Just to incite on this point that everything's implemented in very small modular layers. All of these are available through the Keras NLP library. All this code is open and available. We'll dive into it very soon. Throughout this session, we're going to be looking at how to load in the 2 billion and 7 billion instruction tuned. We'll look at what that means and the normal pre-trained model. We're going to make some chatbots, make it talk like a pirate. We're going to be diving into some pretty cutting edge research and seeing how to implement all of this inside of Keras. So let's try it out. Let's start with basics. We import Keras NLP, our NLP package for Keras, and then we're going to just do from preset for our Gemma instruct 7B English. So this is loading up our 7 billion parameter instruction tuned model. What do I mean by instruction tuned? We'll get into how it's trained, but essentially what it does is it takes in full conversations. It's able to take in a model prompt, then a user talking, then a model, then a user, and all of this within its context window. We're going to start by just saying hi. Hi, Gemma. So how does this prompting work? When you want to add in the full conversation, what we want to do is use this conversational markup. So in this case, you want to say start of turn user, then enter in the start of turn model, and you interlace each of these. So first one, then the other. And then every time you call Gemma, you're going to want to add in that whole context so that it is able to appropriately answer what it needs to. Martin is now going to talk us through the chatbot demo.
All right, let's switch to the demo, please. So all of the demos we'll be showing you today are available. This is in Colab. You see the URL. You can actually run this at home. In this demo, I'm running, just for the technicalities, I will be using the 7 billion parameter model, which is pretty large. I'm running it on a TPU device, tensor processing unit, which has 8 cores. So here are my 8 cores that loaded. And as Gabriel said, Keras is a high-level library that works on top of a lower-level mathematical library, which today can be either JAX or TensorFlow or PyTorch. So this line, I'm selecting the JAX backend. So I've run this beforehand up to this point where I'm loading the model. This is the line that loads the model from preset and so on. The model is loaded. It takes a minute. I didn't want you to wait. But from there on, I'm going to run this myself. This class here is the little helper that implements the turn-by-turn tagging. It's just 15 lines of code. That's what helps you tag who is speaking and pass that context back to the model at every question. You can copy-paste it from here into your own applications. And so let's start chatting. What could we ask this model to do? Well, why not chat about prime numbers? So tell me in a few words how to compute all prime numbers up to 1,000. And Gemma answers, use the sieve of Eratosthenes algorithm. All right, that's good. It's very short. So maybe Gemma could generate the code for us. Let's try and ask that. So now in Python. And here is my Python. Since this is a live demo, I want to see if this generated code actually works. Let me copy-paste it into a new cell and run it. And yes, it's actually generating prime numbers up to 1,000. So, but how did Gemma do this? We could try to understand this code line by line, but actually I'm going to ask Gemma to explain. So let's go. Thank you. It works. Can you explain the code in plain English? Here are my explanations. Oh, that's a lot of explanations. This is probably good, but not very readable. I was expecting my explanations to be in the code as comments so that I know at every line what is going on. That's not the formatting I wanted, but let's ask Gemma to format this differently. Great. Now add those explanations as comments in the code, line by line. And here we are. Again, live demo, so I'm copy-pasting this into a new cell. And as a bonus, you get syntax highlighting, and you can actually read the explanations that Gemma has added. It seems to be the actual implementation of the sieve of Eratosthenes algorithm. I think it got that correct. Let's run it again. It's still running. So this is how you implement a chatbot using the Keras API and the Gemma model. Back to the slides, please.
Gabriel.
Just as a technical side, Keras gives you the option to use multiple precision modules. So for example, you can use float32, float16, or a mix of these two, and also int8 if you're looking for some quantization stuff. Why does this matter? Because if you're trying to get a speedup, you can usually get a 2, 3, even 4x speedup just by enabling this one line of code to mix float16. Additionally, when you're working with these larger LLMs, when you're working with a 7 billion model, that is just 17 gigabytes on float16. If you want to half that, you're going to have to use int8. For context, Wikipedia's full text is about 22 gigabytes, so float16s or 32 can be pretty unwieldy. Back for you.
Thanks, Gabriel. Let's talk about fine-tuning Gemma. Gemma is a general model, so if you want it to perform on a specific task or domain really well, you need to fine-tune it. For example, if you want Gemma to perform really well on the translation task, you can fine-tune it on translation sentence pairs. Or if you want Gemma to chat with you like a pirate, you can fine-tune it on pirate speech. Martin will show us how to do that later. You can fine-tune Gemma 7b model in Keras. Gemma 7b is a large model, so let's talk about some techniques that helps us fine-tune the model. The first technique is LoRA, or low-rank adaptation. Instead of training all the model parameters, LoRA freezes the original model weights and only trains 2 lower rank matrices. For example, here, instead of training this big red n by n matrix, LoRA trains these smaller blue matrices. It multiplies them and adds them to the original weight matrix to create the updated matrix. Because in LoRA fine-tuning, number of trainable parameters is significantly smaller than the full model weights, the training runs faster and requires less resources. You can easily LoRA fine-tune your model in Keras. You can enable LoRA for your model by calling the enable LoRA API on the backbone of your causal language model. After fine-tuning, you can save and load your LoRA weights separately. Because LoRA weights are smaller than the full model weights, this makes them transferring and sharing and storing them much easier. The second technique that helps us fine-tune a Gemma 7b model is model parallelism. Keras NLP, Keras has model parallel API, and it abstracts away all the complexities of parallel computation. It allows you to specify how to split all the layers and where to put the pieces. Keras Parallel API is backed by JAX. And so you only need to specify how to split the largest layers, and that are the bottleneck. And the XLA compiler will handle the rest of it. So what the code in the previous slide was showing was that if you have a large block of base like this, you can easily split it across multiple accelerators. For example, if you have a transformer-based model like Gemma, you can split the heads across multiple accelerators. Now, Martin will show us how to fine-tune the chatbot we just built.
So back to the demo, please. All right, what can we fine-tune our model on? This is a demo, so we decided to do something a little bit fun and tune this model to talk like a pirate. So we have a pirate speak data set, and we'll be running our fine-tuning on it and see if this model can pull off a good impersonation of a pirate. So the first thing we are doing here, sorry, not that, is, as Simon has said, enabling LoRa, which means reducing the number of trainable parameters. This cell is just my pirate speak data set. It's already, I loaded it. I'm not actually going to run the fine-tuning. I did that beforehand. It takes about 15 minutes. I didn't want you to wait. But this is the important line in the fine-tuning. I'm just calling the standard Keras model.fit on my data set call. This is what will launch the fine-tuning process on my dataset. I'm also displaying the details of my model down here. And there is one thing I want you to see. It's here the number of trainable parameters. Sorry. So you see there are 22 million trainable parameters in this model. As I said, we're using the 7B model, which actually has 8.5 billion parameters. But those are non-trainable. So this is the LoRa technique in action. It has frozen most of the model's parameters and is fine-tuning just a little subset, 22 million out of 8 billion. All right, so the fine-tuning went well. I did it beforehand. You see the loss going nicely down. And now I'm going to load simply one of those fine-tuned checkpoints and see if we can continue chatting with this model. All right, this is loaded. Let's say hi. Ahoy there. And while this is loading, I actually wanted to show you something else. At the very top here, the code that is doing the partitioning of my model. So as I said, large model, it will not fit on one accelerator. I need to split it across multiple accelerators. For that, I'm using the model parallel API in Keras, which is right here. Keras distribution model parallel. And what this part of the code is doing, you see there are a bunch of regular expressions targeting specific layers in my model. So it's a bit of an art to partition your model. The API allows you to specify layer by layer exactly how you want to split those layers on multiple accelerators. Now, there are people who think about this and do research about how to split the models. So I'm showing you the details. In reality, on the Gemma model, there is a get default distribution API that gives you the settings that usually work, and you don't have to figure out those details yourself. If you want to, it's fully available too. So you have to do this, model parallel setup before you load your model, so that when you load your model, it ends up on multiple accelerators, and you can run it thanks to the shared memory of all those accelerators. All right, back to chatting. So I was just telling Gemma, ahoy there. And it answered, what is it? Yeah, it's right here. Ahoy, it's nice to meet you. What would you like to talk about? That looks like a pirate voice. So, what can we talk about with a pirate? Why not prime numbers? So, yeah, prime numbers for sure. Or that'd be a very interesting topic. Do you have a specific question about them? Well, you see, it's in character. So what can we ask as a specific question? Well, I want to see if this pirate can code. So let's go. Yeah, give me Python, computing them primes up to 1000. Here will be some Python code. And it's giving me the Python code. Live demo again. I want to make sure this is still working. Let's copy paste this code into a new cell, run it, and yeah, those are my prime numbers from 1 to 1000. So as you see, the pirate can code, and it stayed in character to the end. You see there's some nice pirate speak here. So this is fine-tuning in Keras. Back to you, Samana.
Thank you, Mike. Can we go back to the slide? Thanks. So far, we showed you how easy it is to use Keras. You can easily load Gemma model in Keras, and you can build a chatbot with it. You can fine-tune it with LoRa, and you can distribute the model using the Model Parallel API. In the second part of this session, we want to talk about the flexibility of Keras. We want to show you that in addition to very routine tasks such as fine-tuning and building a chatbot, you can use Keras to implement state-of-the-art machine learning techniques. Here we focus on two recently published research papers, control vectors and self-extend. We've chosen these approaches because they are very powerful techniques and they are also very useful. The first one, control vectors, is similar to fine-tuning. It's something to change the model behavior. But the difference is that in fine-tuning, you need to retrain all the parameters. So it comes at a high computational cost. But in control vectors, you only guide the model output into the desired behavior, and it doesn't require any retraining. Self-extend, the second technique, is a technique for extending the context window of an LLM without any additional training. So this self-extend method is helpful when your task requires understanding longer sequences of text. Let's dive deeper into these approaches. The first one is control vectors. So prompt engineering and fine-tuning are two commonly used approaches for changing model behavior. Control vector is a new technique for doing that. Control vectors directly manipulate the internal activations of the model during inference. The main idea is that if you feed a sentence through the model that has a specific tone and you observe the intermediate activations of the model, and then you feed another sentence that has the opposite tone, the intermediate activations of the model are in the opposite direction. Let's walk through an example together. For example, imagine you want to build an AI assistant chatbot for a car dealership, and you want this AI assistant to have a very formal and sophisticated tone. The first step is to create a set of opposite sentence pairs. First, we take a set of neutral sentences. A neutral sentence is something like, the sun is shining. And then we prefix these neutral sentences with positive and negative controls. A positive control is a sentence that drives the model behavior towards the desired direction. For example, in the car dealership example, a positive control can be something like, you are a luxury assistant making a statement about the world. And then we add our neutral sentence. A negative control is something that drives the model behavior towards the opposite direction, towards the undesired direction. A negative control here can be something like, you are a teenager with bad manners and making a statement about the world. When we create these opposite sentence pairs, we feed them through the model, and record the activations of the model when the model is completing these sentences. For example, with the Gemma model, which is a transformer-based model, we record the output of the activations of the decoder block, for example, vector A1 through A4 here. When we record these activations, we can see that these opposite sentence pairs create opposite directions in activations. We can extract these activations using statistical analysis techniques such as PCA. These directions are control vectors, and we have one vector for each layer. Now that we know what's the direction of the model when it's talking about, when it's talking in a specific tone or voice, for example, when it's talking formally, we can push the model towards that behavior by adding the control vectors related to the formal voice or the sophisticated voice. We can even control how strong the effect is by using a multiplier. Now, Gabriel will show us how to implement control vectors in Keras.
Thank you, Sunander. So there are two things that we're going to be doing for this method. We're going to first extract the control vectors. So we're going to grab all those activations, store them in a separate output. In this case, it's going to be an activations output. And then later on, we're going to re-inject them. We're going to just legitimately just sum them. How do we do this? So our first part, extracting the control vectors. In RB4 picture, this is just a plot of the Keras layers. One of the most powerful parts of Keras is this functional model, the functional API graph, where you can grab each layer, manipulate them however you want, add new inputs, add new outputs, and just create a fully new backbone in this case. So for us, we're going to go through each of the layers. We're going initially, Gemma is just like all LLMs, a series of layers. First our input, then our embedding, then our decoder blocks. Eventually, we get to our output. And we're going to grab all the outputs, so it's layer.output for loop through. And we're going to create this kind of activations stack, which is just a stack of all of the inner activations for our model. Later on, we're going to re-inject that. So how are we going to do this? In this case, we're going to use these wrapped layers. We'll show you how to do this. All this code is going to be available, fully multi-backend. Once again, TensorFlow, JAX, or PyTorch. We wrap our layers, which is going to just eventually sum in whatever we learned through our PCA, all that math that Samana was explaining, and then we'll run it. So let's go on over to the demo. All this is available. Our bit.ly links will be on the slides, of course. We install Keras NLP before anything. And then, just to drive this point home, everything we're doing is fully multi-backend. We are not running only JAX code or only TensorFlow code. We are doing JAX, Torch, and TensorFlow code, and I guess NumPy. To change the backend to TensorFlow, for example, we could just Control-C, Control-V, you're done. You are now running this in TensorFlow. Let's go back to JAX, because that is one of our backends. I already pre-ran this because we're on a T4. This is a free tier GPU. So you can run this at home for free with a free Google account. If not, feel free to sign up. T4 gives you about 16 gigabytes of GPU RAM, which is more than enough to use a 2 billion parameter Gemma model. So we pre-run this. Another thing to inside is that we're using these Kaggle usernames and keys just to be able to grab that model. Otherwise, you'll have to add it in the secrets tab. Here are our utilities, just to display everything nicely. We're using the same chat state that Martin was using previously. No differences there. We're going to load our instruction tune 2B 1.1 model. 1.1 it was just a model update a couple of weeks ago. Instruction 2B meaning that it takes in all these conversational prompts. It's able to do turn by turn by turn conversations. So let's set the scene. You are a used car salesman. You're trying to get people interested in your cars, come to your website, and have them finally make a sale, right? So you're going to give your context to the model, to Gemma. You're going to say, hey, I have a Lexus and 2 Hondas. And then if we chat with this, let's pre-run a couple of these cells just so that we can see the output. Again, this is completely free tier Google Colab running on T4, no high RAM, no anything. If we ask it factual questions, what is the first car in the listing? It answers correctly. It's an Lexus RX. Et cetera, et cetera. Third question, most affordable, priciest car. And then we get to something very interesting. We are asking Gemma for its opinion. Again, we're trying to sell these cars. So what would Gemma recommend to your users or for whatever you're trying to fine tune? for what they should buy. So in this case, which one of the three would you recommend for a family of four doing lots of school commutes and the occasional trip to the mountains? And so Gemma answers, the Honda CR-V appears to be the most suitable option. If I walk into a car dealership and the dealer says, the most suitable option for you is probably that car, I am not buying a car, right? So how do we take Gemma and put it in a position where it's able to answer these questions with maybe a bit more passion, right? You can also, of course, follow up because we're adding in all of the context of the turn-by-turn conversation. So in this case, why is this important? It strikes a harmonious combination of features and price. So let's go through the actual code for this. This is everything that we explained in the theory. This is how we generated the plots. In Keras, it is a one-liner, keras.utils.plot model. A little bit of rewiring, but that's just to clean up the plot. You're still going to be able to do it. This is our LLM. I'm not going to go through all of this, but this is exactly the same as what we had on the slides. No differences. We stack in each and every one of these activations. We grab the activations from each Gemma decoder block, and we output it to our stack. And then that stack is where we're going to grab all the numbers, we're going to run our math, and we're going to be able to push our model where we want it. So here is our prompts. I pre-run this because it takes about 4 minutes on a T4 free tier. If you are willing to go for an A100, it's going to be maybe a minute and a half. So I'm not going to run this too much. But essentially, these are all going to be the same prompts as what we saw in the slides. It's going to be first a sentence saying, pretend you're a luxury assistant, which pushes the model into one of the directions we want, and then your FoulMouth pushing it in the other direction. We're going to go down here. This is how we extract it. The important part is here. All of this is building up to running through our new backbone, the thing that we rewired, creating this new stack. And here's where we can extract those activations. So to run something in Keras, all you do is call the model that you've created, in this case, new backbone, pass in your process prompts, and you're done. There we extract it all. We do our PCA. I'm not going to go into the math. All this code is available. It's extracting everything. Then here we get to our control vector decoder layers. This is what we did later on for step 2 to re-inject, to add in what we wanted into our model. I'm not going to run here. And here we get to our actual demonstration. So we've done all of this. We have a vector that positions us in either a formal place or an informal place. Based on this, we can push our model. So let's start out by giving it informality. So we set our formal voice to -1.9. Let me pre-run all of these. Again, this is all live. They're taking about 5 seconds on a free tier T4. Factual questions all correct, just double check. And then we're going to get to our opinion. Which one of the 3 cars would you recommend, so Gemma, after having fine-tuned, for a family that does a lot of school commutes and the occasional trip to the mountains? And the answer is informal. It's the best car for a family is gonna be the one that's reliable. We have made our Gemma model informal, more human, something that we would potentially be able to talk to better. If we ask it to elaborate, we see it even more clearly. For safety features, you want a car that has good safety features because you don't want to get into, it cuts off because we cut it for the demo, but you can have it keep on generating text. And all this is very, very informal. And with no changes, just with what we've already generated, let me pre-run over here. Here we see the other direction. So we've just reversed the minus sign and converted it to 1.9. We add in the context of all 3 cars. We ask it as questions, is correct, second car, third car. And then while we wait for it to run, we see which of the 3 would you recommend for a family of 4 doing a lot of school commutes and the occasional trip to the mountains. And now, let me double check that we ran every cell. Yes, this is through. There we are. While we wait for all of this to run, let us go back to the re-injection, and we see this very important line. This is where we're doing that sum. This is what it all built up to. It's essentially just summing in our self.control vector through our Keras layer model. And then as this has finished to run, okay. Back to our opinion-based thing, we once again get the appears to be the most suitable option, but once we ask it to elaborate on this question, it is able to be a formal, good salesman. The Honda CR-V strikes a harmonious balance between practicality and luxury, offering a compelling combination of features. As you can imagine, if you are able to send more GPU, more examples, more compute into this, you can get it to do anything you want using the same exact prompts that we used before, just with this control vector system. And we're going to go to the theory for the second one.
Thank you, Gabriel. All right. So this was one pretty advanced paper that we implemented in Keras. We wanted to show you another one, which is called self-extend. This one solves a different problem, the problem of context. Gemma was initially trained with a context of 8,000 tokens, which means that if you are running a technique, for example, like RAG, retrieval augmented generation, where you have to put a lot of documents in the context for the model to answer in a knowledgeable way, you might be limited. And this is the problem with large language models. Their context seems to be fixed. It's what they have been trained on. Not so. This self-extend paper actually shows us how to extend it by hand by doing a bit of brain surgery in the model itself. To understand how it's doing it, we actually have to dive into the core algorithm that is running in a transformer model, and that is called self-attention. So let's get into it, and you will see if we understand what self-attention does, fixing this context problem is actually pretty easy. So self-attention is a mechanism that computes all the possible word combinations in your prompt. And that is what helps the model reason about which words are in the prompt and how they interact. So the way it is computed is by the time we get to computing self-attention, our sentence is already transformed into vectors, one vector per token. Here is one vector per word. And since we want to compute the interactions between words, we actually have one set of vectors in red here that represents every token in the sentence, and a second set of vectors that represents the same sentence with the same words, but here in green. And self-attention is simply all the possible dot products between those words. It's a matrix of all possible combinations. But there is one additional ingredient. It's what you see here in the equation as Rho of n minus p. It's called rotational positional encoding. So I'm not going into the math, not explaining why it's called rotational. This is the part that encodes the relative positions of the words. Because of course, it's not just because two words are in the sentence, you also need to know how far they are apart and so on. If I have the words, for example, common and sense, if they appear next to each other, it's common sense. And that has a specific meaning, right? So this positional embedding depends on n minus p. N is the position of one word and p the position of another word. So n minus p is the distance between words. And this is the ingredient that is going to be problematic with respect to context. So let's try to see what kinds of distances between words I can get in a given prompt. I have them here in this little green matrix. And let's see what happens if now I'm running my inference on a prompt size that is bigger than the context the model was trained on. So what is happening is those numbers in red. Suddenly, word distances appear that the model was not trained on during training. And this is going to be problematic. It's not trained to handle such long word distances. It is going to output gibberish if it encounters this. How to fix it? Well, the super clever solution that this paper found is just use smaller numbers. No, really, that's it. If you understand what is going on, you can fix it easily. You have to be just a little bit careful. So let's get back to this matrix. We want those numbers in red to come back to the range that was seen during training. But you have to be careful at close range. Exact distances between words matter. So we have to keep those in place. We can't change those. At close range, if I say common sense, that has a certain meaning. If I say common comma, in a sense, different meaning. Still the same words, just the distance is different. But at long range, which is where my problematic long distances are, I can just change those numbers and use smaller ones, a bit of interpolation so that the relative positions are good, and that's it. With this bit of surgery, I'm suddenly fixing the context length of my model and I can extend it. So now we want to see how to implement this in Keras on a pre-trained model that you loaded from Keras NLP. Go ahead.
Thank you, Martin. So we might recognize this code from a few minutes before. This is the same patching system that we were using before for our context, for our other demo. What we're doing here is we're simply going through all of our layers. We're overriding our two methods, in this case, our rotational positioning embedding, or ROPE for short. And we're overriding our compute attention with something called extend compute attention, which we'll see throughout in the demo. Just inside on this, the reason that we have to get rid of the rope is because when you actually do this whole gemma, first you do our positional embedding, then we do attention. To make all this easier, let's get rid of our rope, put it all in the attention. And let's go to the demo, see how this is done. So we start by installing the latest Keras NLP. I've already pre-run this. We're going to be doing all of this on an A100. The reason we're not doing this on a free T4 is that we're trying to really push the capabilities of Gemma. Gemma was not trained for any of this. Gemma was trained for going up to about 8,000, a bit more than 8,000 tokens. And we're trying to push that. We're trying to get to 10,000. Potentially, you could get to 20, 30, whatever you have the compute, the GPUs for. Once again, we're going to be using JAX, but fully multi-backend. Want to use TensorFlow? TensorFlow. Done. Let's go back to JAX. This is all pre-run. We're using our Kaggle username and key. We're installing the same, grabbing the same Gemma. So this is the Gemma 1.1, instruction 2B English. It loads up. Colab is very helpful with this in that it has it all cached. You're not downloading anything. It would run in about 20 seconds. So we're a car dealership. We have about 150 models of cars, 200, 300, some very large number that's very difficult to work with. And we're trying to use our open source models, our Gemma powerful models. In this case, we want our users to be able to request whatever piece of information they want. In this case, the 2024 Google I/O car discount code, which is 1234123. This is not a real car, just for disclaimer purposes. This is our haystack. We have a haystack of 45 cars, and we're trying to hide our needle, in this case, that discount code. So let's run through this. Until here. So we're going to be using the same conversational system. We're going to be using the start turn user, start turn model. And let's start out with just 45 cars as context. So that's about 2,700 tokens, which is still a lot. I mean, 45 cars are a decent amount of cars, but it's well within the range of Gemma's capabilities. So in this case, we ask it for the discount code, and it answers 1234123. As a cool technical note here, one of the things that we do is we do our user turn first. So what is the discount code? We end our turn, and then we start the turn of the model with the discount code is, so that we're already preloading it with what we potentially would want to see. So let's try and do something that is not within Gemma's capabilities. Let's quadruple the amount of cars. So we're at about 200. We're running it with 10,000 tokens, a bit north. Gemma was not trained for this. It is going to fail. And that is fine, because we have self-extend to come to the rescue for this. So we just get an enter and a the. That is fine. This is not expected to work. Now, we're going to get into our self-extend method. We're not going to go too much into it. We've gone through the theory. That is just implementing this. All of this will be available later on. This is the code from the slides. We're just overriding our rope method, nulling it out, and adding our new extend compute attention, which is what we just defined. We're going to recompile this all, double check that it does work. So this is all running live, once again on an A100. It's going to answer to a hi there prompt. And we're going to see, in this case, the full output. So as soon as this runs, it's having to recompile. It's having to do everything. JAX is a compiled backend, meaning that it's going to have these static shapes. And there we are. Here we see the actual full output. So start of turn, it answers to hi there. Start of turn model. Hello, it's great to hear from you. What would you like to talk about? It's working perfectly fine. Now, let's test it with a self-extend algorithm. So let's begin with something that is within old Gemma's capabilities. So in this case, we're going to be using about 8,000 tokens. That's the tripled haystack, meaning we're using about 150 cars, still a lot. Let's let it load. And remember, this is all running on that A100, so we're able to do these very long conducts in full control for us. So it answers correctly. The discount code is 1234123. Awesome. Let's push it further. Let's see if Gemma is able to do something that it was not trained to do. So we're going to quadruple this. See how we're at 10,639 tokens. That's about 2,000, 3,000 more. You can push this much further. For this purposes, we'll keep it at 10,000. It ran in about 5 seconds and it's able to answer correctly. The discount code is 1234123. Now Martin's going to send us off.
Thank you, Gabriel. Can we go back to the slides, please? All right. So this is what we wanted to show you today. We wanted to show you how to do simple things with Keras by loading a model from Keras NLP and implementing the basic workflows like the chatbot, like fine-tuning it as well. But we also wanted to show you, all of those things in Keras are basically one-liners. But we also wanted to show you that Keras is a full-fledged modeling framework. The entire architecture of the Gemma model is implemented in Keras using Keras layers. And when you load a model from Keras NLP, the entire graph of layers is available to you if you need it to change the behavior of the model to implement the latest and greatest research papers on your model. Keras offers you that flexibility in addition to being super easy to use for the easy tasks. That's it. We hope you enjoyed this session. If you need to go back to the 3 demos we showed you today, you have the links here. And I just have to thank you for your attention.